Hi everyone, this is Professor West, and we're going to be doing 3.5 and 3.6, which is rational functions and their graphs. I would like to ask you to bear with me, as writing on my iPad is not as good as writing on paper or on the board. So anyway, we are going to start with the definition of a rational function. So, rational function. Okay, so we're going to let P and Q be polynomials where Q of x doesn't equal 0, then f of x equals P of x over Q of x is a rational function. So this means that rational functions are just functions that have polynomials in the numerator of a fraction and in the denominator of a fraction. And an important aspect is this Q doesn't equal 0 part. That will help us find our domain, which is going to be our first example here. Okay, so example. Find the domain of the following rational functions. Find the domain of the following rational functions. Part A. F of x equals x plus 5 over x minus 8. F of x equals x plus 5 over x minus 8. So we know that Q of x, which is x minus 8, cannot be equal to 0. So 0 cannot equal x minus 8, which, if we solve for x, means that x cannot equal 8. So what does that mean for our domain? Well, it can be any number except 8. So I can go from negative infinity to 8 union 8 to infinity. So that's my answer there. So my domain is everything except 8. Okay. Let's do part B. G of x equals 1 over x squared minus 6x minus 55. So g of x equals 1 over x squared minus 6x minus 55. So we know that the denominator, x squared minus 6x minus 55, cannot equal 0. So we're going to go 0 cannot equal x squared minus 6x minus 55. Now this is a quadratic function, so we can factor it. It is factorable. So I would ask that you take a moment, pause the video here, and see if you can factor it. Alright, so hopefully you paused the video and you factored it, and you saw that 0 cannot equal x plus 5 times x minus 11. So this means 0 cannot be x plus 5, and 0 cannot be x minus 11. So now, if we solve for these, we get x cannot equal negative 5, and x cannot equal 11. So what would this be as a domain? Well, it can be everything except negative 5 and 11. So I'm going to go negative infinity to negative 5, union, negative 5 to 11, union, 11 to infinity. This here shows every number except negative 5 and 11. So that is our domain. All right. Finally, we have part C. Oh, and let me scroll up so you can see the whole thing there. But anyway, part C is h of x equals x plus 2 over x squared plus 1. X plus 2 over x squared plus 1. So let's try it out. So we know that 0 cannot equal x squared plus 1. Now if I subtract 1 to the other side, right, I get negative 1 cannot equal x squared. Now if you take a moment and think about numbers that you can plug into x squared, you'll notice that they are all either 0 or positive. So that means that this here is always true, right? This is always true when x is a real number. If you can't plug in an imaginary number, then it's always true. So always true for all x in the real numbers. So what does that mean if it's always true for all x in the real numbers? Well, that means there's no real number that I can plug in that would make this denominator 0. So, since there's no number that I can plug in to make that denominator 0, it must be that our domain is all real numbers. So that means that it's going to be from negative infinity to infinity. We'll box that up. So now we can find the domain of rational functions. So let's talk about vertical asymptotes. Okay. So vertical asymptote. So the vertical line x equals c is a vertical asymptote of the graph of a function f if f of x approaches infinity, or f of x approaches negative infinity as x approaches c from either side. Okay. So I think it's a little bit easier to see this visually. So I have the 4 types of vertical asymptotes for us to see. Okay. So we have types of vertical asymptotes. And there are 4 types, so let's draw them. Okay. Alrighty, so here I have my x-axis and my y-axis, 0. And then I'm going to have my vertical asymptote here. Okay, it goes on forever, up and down. It's at x equals c here. That's the line, x equals c. And I'm going to be reusing this multiple times, so I'm just going to copy that real quick. Okay, so one of the types is that we don't really care what goes on over here, so I do the little dash, and it will go up forever. And the other side, dash, 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 will also go up forever. So both of them approach infinity as x approaches c. Okay, and then let's get another one out here. Feel free to pause the video to draw this and get it set up. But another one, if they can both go to infinity, well, they can both go to negative infinity. So I can go like this. They both go to negative infinity. So you can see the graph is just going up, approaching it, but not ever crossing. Okay. And then there's 2 more, so I'm just going to get those ready. And again, if you need to pause the video to draw them yourself, feel free to do so. Okay, something like that. And then something like that. Okay. So another one is that you could have it go this way, and then have the other one go this way. So you can go towards infinity from the left and towards negative infinity from the right, or you could go like this, where this one goes down, but this one over here goes up. Maybe I redraw that one a little bit better, because we don't really care what happens on the other parts of the graph, just what happens at the vertical asymptotes here. So they can either both go to infinity, both go to negative infinity, or they can have a combination of the 2. So those are the 4 types of vertical asymptotes. So now we're going to talk about vertical asymptotes of rational functions more specifically. So, vertical asymptotes of rational functions. Vertical asymptotes of rational functions. So let's start with consider the rational function f defined by f of x equals p of x over q of x where p of x and q of x are polynomials. So where p and q, I should say, where p and q are polynomials with no common factors other than 1. If for C and R, if for C and R, Q of C equals 0, then x equals C is a vertical asymptote of f. So all we need to do to find the vertical asymptotes of f is set q of x equal to 0 and solve for x, because we really just want to find the zeros of q. We want to find the zeros of q because that is where our vertical asymptotes will occur. So let's try it out, shall we, on an example. So example. Identify the vertical asymptotes of the following rational functions. So identify the vertical asymptotes of the following rational functions. All right. Part A. F of x equals x plus 31 over x minus 17. Okay, f of x equals x plus 31 over x minus 17. Well, we know if we set the denominator equal to 0, that will tell us what our vertical asymptote is. So let's do that. So let's go 0 equals x minus 17. Well, now we want to solve for x. So we would add 17 to both sides, and we'd get x equals 17. So we can say that there is a vertical asymptote, usually I just say VA, at x equals 17. Okay, so vertical asymptote at x equals 17. And then you're done with part A. Let's move on to part B. Part B. This is g of x equals x minus 2 over x to the third minus 7x squared minus 9x plus 63. All right, so just like before, we just want to set our denominator equal to 0. So I'm going to say 0 equals x to the third minus 7x squared minus 9x plus 63. Okay. So this is factorable, so let's factor it. So I'm going to have 0 equals, I'm going to put in my parentheses where they belong. So I'm going to have a parenthesis here, x to the third minus 7x squared plus negative 9x plus 63. So for this first parenthesis here, this first bit here, I am going to take out what they have in common, which is x squared. So I get 0 equals x squared, and what's left over is x minus 7. And over here, I'm going to take out what they have in common, which is a negative 9. And what I'm left with is x minus 7. So now I can factor by grouping, and I can factor out a x minus 7 from both of these. And what I'm left with is x squared minus 9. Now I can still factor this, x squared minus 9. It's a difference of 2 squares. So I'm going to get 0 equals x minus 7 times x minus 3, since 3 is the square root of 9, times x plus 3, because 3 is the square root of 9. Now I can set each of these equal to 0. So I have 0 equals x minus 7, 0 equals x minus 3, and 0 equals x plus 3. Solving for x, we get x equals 7, x equals 3, and x equals negative 3. So this means that there are vertical asymptotes, so I'm going to write vertical asymptotes, VAs at x equals 7, x equals 3, and x equals negative 3. And then you're done. So box that up. So you can even do this with higher ordered polynomials in your denominator. All right. Next, let's move on to part C. Part C. This is h of x equals 3 over x squared plus 6. So h of x equals 3 over x squared plus 6. All right. So we're going to set x squared plus 6 equal to 0. Now I'm going to subtract 6 from both sides so we can see something here. So negative 6 equals x squared. Now I want you to notice something, that this here can never happen in R, right? I would need an imaginary number to make this true, but we're not even going to concern ourselves with imaginary numbers, right? So this is impossible. This is impossible in the real numbers. Impossible in the real numbers. So that means that there are no vertical asymptotes. So we can say there are no vertical asymptotes. And that's your answer. No vertical asymptotes. All right. So that is this example. We were able to find vertical asymptotes, so that's wonderful. Well, if there's vertical asymptotes, you might be wondering, are there horizontal asymptotes? And you would be correct, there are, and we're going to talk about them. So let's talk about the horizontal asymptotes. Okay, horizontal asymptote. So the line y equals d is a horizontal asymptote of the graph of a function f if f of x approaches d as x goes to infinity, or as x goes to negative infinity. Okay. So let's look at the types of horizontal asymptotes, just like we looked at the types of vertical asymptotes. Okay. So we have types of horizontal asymptotes. All right, and there are 4 of them, like before, so I'm going to do that copy paste thing again. If you need to pause the video to draw your 4, that is totally fine. So it should look something like this. Okay. X, 0, y. And then there's going to be a horizontal asymptote. Honestly, maybe it'd be better. Actually, this should be fine. horizontal asymptote, actually I will bring it down a bit. I'm going to do this where I bring this down by 1. Oh, that does not look good. Good enough. And I'm going to grab this and I'm going to bring it down by 1. Just so that way it'll make more sense, but I can draw now, or actually I'll bring it down by 2. Whoops. And grab the x. That way, when I draw my horizontal asymptote, it'll be a lot more room for us. Yeah. There'll be a lot more room for us to see it. Okay. So here's my line, y equals d. Okay. And I'm going to copy this. And like I said, if you need to pause so you can draw this, feel free. Copy. Okay. All right. So the first one we have is that they'll both approach from the top and go on forever. So it might look something like this, but we don't know what happens here. So we'll leave it like that. Okay. Oh. Maybe if I draw the line first. There we go. So we don't know what happens in the middle at all, but we do know it goes on forever. All right. And now, let's see if I have enough room to put it over here. Yes, I do, if I do it like that. Okay. The next option is that if they can both come from the top, well, that means they can both come from the bottom. So maybe something like this. They're both coming from the top, or sorry, they're both coming from the bottom, and they're both approaching y equals d. All right. Next, we'll put this one here. Okay. This one, maybe, no, as it goes to the left, it's approaching from the top. But it's approaching bottom as I come from, as I'm going towards the right, I should say. So I'm going towards the right, coming from the bottom. Right, and we don't know what goes on in the middle. Anything could happen. And then we also have this last one here. I could be approaching from the bottom as I come from, could be approaching from the bottom as I go towards the left, and I could be approaching from the top as I go towards the right. But I'm still approaching the line y equals d. We don't know what happens in the middle. Okay, so these are our 4 types of horizontal asymptotes. Okay. So we should have a quick note. So note. A graph can never cross a vertical asymptote. But a graph can cross a horizontal asymptote. So it's something you need to keep in mind. Okay, It's just something you need to keep in mind. Now, let's talk about horizontal asymptotes of rational functions. Horizontal asymptotes of rational functions. All right, let f be defined by the function and then we have a big function here to write. F of x equals, grab a really long line here, a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus blah 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 plus a sub 2 x squared plus a 1x plus a naught all over b sub m as in Molly x to the m plus b sub m as in Molly minus 1 times x as in x raised to the m minus 1, the m being as in Molly, plus dot 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 plus b sub 2 x squared plus b sub 2x plus b naught. Okay, so we're going to let f be defined by this. Notice this is just like p of x over q of x. It's just that we're writing out the definition of a polynomial. So it's still a polynomial over a different polynomial, even though it looks kind of crazy and funny here. All right, so we're going to let f be defined by this. All right, so this definition of f indicates that n is the degree of the numerator and that m is the degree of the denominator. Okay. Then we have three options. Okay. You'll need to memorize these. These will be really important. 1. If n is greater than m, so if n as in Nancy is greater than m as in Molly, f does not have a horizontal asymptote. F does not have a horizontal asymptote. okay? So if the degree of the numerator is bigger than the degree of the denominator, then f does not have a horizontal asymptote. Okay. 2. If n, as in Nancy, is less than m, as in Molly, the line y equals 0 is the horizontal asymptote of f. So the line y equals 0 is the horizontal asymptote of f. Okay? And 3, if n equals m, then the line y equals a sub n over b sub m, okay, a sub n over b sub m, and that's just these up here, right? It's just the leading coefficients of your numerator and denominator, okay? Just the leading coefficients. So the line, this is the horizontal asymptote of f. Okay, and that is our 3 options, right? Either the numerator can be bigger than the denominator, then there just isn't a horizontal asymptote. The numerator could be smaller than the denominator, then it's just y equals 0. And if they're the same, then it's the ratio between the leading coefficient of the numerator and the leading coefficient of the denominator. All right, so before we get into an example, we're just going to have a quick note. So note, rational functions can have multiple vertical asymptotes but can only have at most one horizontal asymptote. All right. So you can have multiple vertical asymptotes as we saw above, but you can only have either one or no horizontal asymptotes. So let's do an example. Find the horizontal asymptote of the following rational functions, if any. Find the horizontal asymptote of the following rational functions, if any. Redo that y. There we go. If any. Part A. f of x equals 2x squared minus 7 over 3x squared plus 1. F of x equals 2x squared minus 7 over 3x squared plus 1. So the first thing we want to do is find the degree of the numerator and the degree of the denominator, and then we want to compare. So we have the degree of the numerator. So we want to find the degree of our numerator. Okay. So the degree of our numerator. So if we look at their numerator, this is our leading coefficient, or sorry, our leading term, my bad, which means this is our degree. So our degree is 2. Next, we want the degree of our denominator. So if I look at my leading term, I can see that my degree is also 2. So that means these are the same. They're equal. So let's look back at what that means. What does it mean if they're equal? So I scroll up here and I look at my 3 cases. I'm going to look for the one where my degrees are equal. That's this one here. So this tells us that the horizontal asymptote is going to be at the line a sub n over b sub n. So let's go back down. So what's a sub m, right? So we want to find our answer. So there's going to be a horizontal asymptote. So horizontal asymptote, you can just call it HA, at y equals. Now we want the leading coefficient of our numerator. Well, that's just 2. Over the leading coefficient of our denominator, that's 3. So that means there's a horizontal asymptote at y equals 2 over 3. And then you're done. So if they're equal, then you're just going to do the leading coefficient of the numerator over the leading coefficient of the denominator. All right, let's try part B. Part B is g of x equals 5x to the 7th plus 4x over 2x minus 1. So we need to find the degree of the numerator So the degree of the numerator is, take a look, make a guess. Yes, it's 7. And then the degree of the denominator pause the video if you need to, look at the denominator, make a guess of what the degree is. It's 1. So which one's larger, the numerator or the denominator? The numerator. So numerator is larger. So if the numerator is larger, well, let's go back to the horizontal asymptotes of rational functions, right? Let's go back and see what that means. So if you remember, our numerator goes by n's as in Nancy, and our denominator goes by m's as in Molly. So we want the one where n is bigger, and that looks to be like number 1. So number 1 says if n is greater than m, right, then f does not have a horizontal asymptote. So that means there's just no horizontal asymptote. So let's go back down here. And since the numerator is larger, all we have to do is write no horizontal asymptote. And then you're done. Okay? So that's part B. So let's do part C. Part C. We have h of x equals six x to the third plus 5x squared, 5x squared minus x plus 8. And in our denominator, we have 4x to the fifth minus 3x to the fourth plus x to the third minus x squared plus 2x plus 7. Okay. Kind of a long one, but feel free to take your time, pause the video, write it out. All right, so first we need to find the degree of the numerator. Okay, and if you look at the numerator, the degree is 3. And then we need to find the degree of the denominator. If you look at the denominator, the degree is 5, which means this time the denominator is larger. Right, so if we take a second here and scroll back up, this means we want m to be bigger. So that would be number 2, which means that the line y equals 0 is the horizontal asymptote. So if we go back down, we can say that there's a horizontal asymptote at y equals 0, and then you're done. So this example kind of highlighted all 3 methods, like all 3 cases, I should say. Okay, one where they're equal, one where the numerator is larger, and one where the denominator is larger. So now we're going to want to talk more about finding things to help us graph, because these will help us graph, right? Knowing our horizontal asymptotes will help us graph. Knowing our vertical asymptotes will help us graph. But being able to find like y and x intercepts, those will also be very useful. So let's talk about it. So here we're going to talk about y-intercept of rational functions. So y-intercept of rational functions. Okay, so for a function f defined as then we'll have, I didn't really set myself up for success here. I'm just going to put this on the next page. Okay, defined as f of x equals p of x over q of x, where p of x and q of x are polynomials, so where p and q are polynomials, such that q of x doesn't equal 0, the y-intercept of f occurs at f of 0 so it occurs at f of 0, and we'll write it as an ordered pair when we do it. So we're just going to plug in 0 to find our y-intercept here. And then x-intercept, right? X-intercepts of rational functions. X-intercepts of rational functions. All right. So for a function f defined as f of x equals p of x over q of x, where p and q are polynomials, such that q of x doesn't equal 0, the x-intercepts of f occur when p of x equals 0. So they only occur when the numerator equals 0. All right? So here you can look at both the y-intercept of rational functions and the x-intercept of rational functions. I'm going to have a quick note here. Okay. Note. It is possible. So it is possible for a rational function to have no x or y-intercepts. Okay, so it's possible for a rational function to not have any due to having asymptotes, right? So they might not have any x or y-intercepts due to asymptotes. Okay? So let's do an example. Okay? Example. Find the y-intercept and x-intercepts of And then we have f of x equals x squared minus 16 over x plus 2. Okay. So let's start with our y-intercept. So all we do, just plug in 0. So we're going to go f of 0 equals 0 squared minus 16 over 0 plus 2. Okay, so that will end up being 16 over 2, which just equals 8. So that means our y-intercept is at, oh, I made a mistake. We should have a negative 16, so negative 8. My bad, my bad. So instead of 16 over 2, we should have gotten negative 16 over 2, right? Negative 16 over 2, which gives us negative 8, right? But we have to write our final answer as an ordered pair, so that means it will be, since it's a y-intercept, 0, negative 8. And then we're done. Okay. Next, we'll do our x-intercept. We might have more than one. Okay. X-intercepts. So we take our numerator and we set it equal to 0. So I have 0 equals x squared minus 16. All right, well, this looks like a difference of 2 squares. So I have 0 equals x plus 4 times x minus 4. So that means I have 0 equals x plus 4 and 0 equals x minus 4, which means I get x equals negative 4 and I get x equals 4. So I want to write these as ordered pairs. So I'll get 4, 0, oh, negative 4, 0. Oh, let me just rewrite it all the way. Negative 4, 0, and 4, 0. Right. And then we were able to find both the y-intercept and the x-intercepts of f. All right. Last but not least, we want to kind of combine all the information that we just learned and graph some rational functions. So I'm going to start by writing out the example prompt, and then you'll notice some cuts in the video as I prep us for graphing the functions when we get to the point where we're going to graph them. All right. So we're going to start with example. Graph the following rational functions. Oh, I put that a little bit low, didn't I? Oh well. Graph the following rational functions. Part A. We have f of x equals 2 over x minus 3. 2 over x minus 3. So we're going to want to find the x-intercepts, the y-intercept, the vertical asymptotes, and the horizontal asymptotes. We want to find all 4 of those, and those will help us when we graph. So, my bad there. We're first going to want to find the y-intercept. So let's look for the y-intercept here. Okay, so to find the y-intercept, we just do f of 0. So f of 0, that's just going to be 2 over 0 minus 3. 2 over 0 minus 3, that's the same as 2 over negative 3, so negative 2/3. So that means that I'm going to have the point 0, negative 2/3 as my y-intercept. Okay, so now let's try our x-intercepts. Well, you'll take your numerator and set it equal to 0. Now notice this isn't true. So that means that there are no x-intercepts. So we got something immediately that's not true. Okay, so we have a y-intercept and we have no x-intercepts. The next thing we're going to want to find is if we have any vertical asymptotes, right? So vertical asymptotes. So if I look up here, I'm just going to set my denominator equal to 0. So I have 0 equals x minus 3, which will give me the line x equals 3. So I know I have vertical asymptote at x equals 3. Now I want to see if there are any horizontal asymptotes. I want to see if there's any horizontal asymptotes. So if I look up here, I need to figure out the degree of my numerator. The degree of my numerator is 0. And I need to figure out the degree of my denominator. The degree of my denominator is 1. 1 is bigger than 0, so that means the degree of my denominator is greater than the degree of my numerator. So that means I have a horizontal asymptote at y equals 0. Okay, and we can only have one horizontal asymptote, so I don't know why there's an s there. Horizontal asymptote at y equals 0. So we are now going to use all the information that we have here to graph. Okay? So I placed a grid down here so we're able to graph. So the first thing we're going to want to do is graph our vertical asymptote and our horizontal asymptote. So I'm going to do that in a different color than my actual graph. So I have a vertical asymptote at x equals 3. So I'm going to go to x equals 3 and I'm going to draw a nice dashed line here to signify that I will have a vertical asymptote there. So I know when I graph where it will be. Okay, and then I also want to put my horizontal asymptote at y equals 0 down. So I'm just going to put one there as well. Now, I'm going to let you know that the only graphs that we're going to care about in this class for like exams and whatnot are the ones that either look like this, so they'll look like this, or they'll look like this. So we need to figure out which one it is. But to do that, that's where our x and y-intercepts come in. We don't have any x-intercepts, but we do have this y-intercept here at 0, negative 2/3. So if I look over here, I'm going to go 0, right, 0, negative 2/3. So it's going to be like here-ish, right? It doesn't have to be perfect. But just having that there tells us that it's going to be the one that looks like this, right? It's not going to be the one that looks like this because we have a point over here. So we know that our graph's going to look, oops, I'm so sorry about that. And let me like lock my screen here. There we go. So we know it's going to look something like this, and it does not have to be perfect at all. I'm just going to like kind of make it look like it's approaching my horizontal asymptote here. And I'm going to try to hit my mark, and I'm going to come down, make it look like I'm approaching this here, right? And then similarly, I'm going to definitely have the one that comes like this over here, going like that, this way. Okay. And so that is our graph here. Okay, it doesn't have to be perfect. I mainly just want to see the dashed lines where you have your horizontal and vertical asymptotes, and I want to see those, those intercepts wherever they are. I'd like to see them. Okay, so this looks good here. Let's move on to part B. And now we're going to do part B, which is g of x equals 5x plus 10 over x minus 1. So our first step is to find our y-intercept. Okay? We want to find our y-intercept. So, to look for our y-intercept, I'm just going to do g of 0. Okay, so that's just going to be 5 times 0 plus 10 over 0 minus 1. So that just ends up equaling 10 over negative 1, which just gives us negative 10. So we have our y-intercept at negative 10. So then we're going to want to do our x-intercepts, if there are any. Okay. We want to do our x-intercepts if there are any. So we're going to just set our numerator equal to 0. So 5x plus 10 equals 0. Subtract 10 from both sides. I get 5x equals negative 10. Divide both sides by 5, and I get x equals negative 2. So we have an x-intercept at negative 2, 0. So those are our intercepts. We're then going to want to do our vertical and horizontal asymptotes. So we have vertical asymptotes. So we just set the denominator equal to 0. So I'm going to go x minus 1 equals 0. So x minus 1 equals 0. That just means I get x equals 1 as a vertical asymptote. And then we have our horizontal asymptote, if there is one. Means we need to find the degree of the numerator, and then also the degree of the denominator. The degree of the numerator is 1. The degree of the denominator is 1, which means they're the same. So that means we're going to have a horizontal asymptote of y equals 5 over 1, which is just y equals 5. Y equals 5. Okay. So now, I forgot to write this as an ordered pair. That's okay. 0, negative 10. So now we're going to graph. So let's start by graphing our vertical asymptotes. So a vertical asymptote at x equals 1. So we're going to go here and we're going to write a vertical asymptote here at x equals 1. And then we have a horizontal asymptote at y equals 5. So we are going to go and write y equals 5. Okay. So now, again, we're at the problem where does it go like this or does it go like this, right? So let's put in our y-intercept and our x-intercepts. So we have a y-intercept at 0, negative 10. So I'm going to go on here, 0, negative 10 is my y-intercept, yeah? So right here, I have a y-intercept at 0, negative 10. And then we had an x-intercept at negative 2, 0, negative 2, 0. So you can see I have stuff over in this corner, so it probably looks something like this, right? it will probably look something like, let's see if I can draw this. Probably will look something like this. And again, it doesn't have to be perfect, which means that the other side probably has something similar like this. Right? It's always opposite corners. Okay? And then you're done. All right? So this is how you would graph part B. Again, doesn't have to be perfect. So now, let's move on to part C. I'm going to set you up for part C, and then I'm going to leave it as a challenge problem, and you're going to upload your solution to the challenge problem to show me that you watched the whole video. So let's do part C. Let's get at least started. So part C. Part C is h of x equals 1 over x plus 6 minus 3. So we have this pesky minus 3 over here, which is not very helpful for us. So I'm going to help you set it up, and then once we get it set up, I'm going to have you graph it yourself. So if we want to graph this, we're going to need to get our denominators to be the same. So I want to rewrite this. So this is going to be h of x equals 1 over x plus 6 minus 3 times x plus 6 over x plus 6. We want them to end up being the same. Okay. So I'm going to distribute my negative 3 through my numerator. So I get h of x now equals 1 over x plus 6. And then I'm going to get minus, and this is over x plus 6, 3x plus, and then 3 times 6, which is 18. Okay? And now I'm going to distribute my negative sign through. So I have h of x equals 1 over x plus 6 minus, plus negative 3x minus 18 all over x plus 6. Now we can finally combine into a single fraction. So now I have h of x equals 1 over, it's not just 1 over, but x plus 6. So this would be 1 minus 3x minus 18 over x plus 6. Combine like terms here, and we get h of x equals negative 3x minus 17 over x plus 6. And then your challenge is to graph h of x. But what I want you to see is that we started with this, which was going to be difficult to graph. So instead, we were able to convert it into a single fraction. So hopefully that will help you. All right, this was all of the anticipated 3.5 and 3.6. And I'll see you guys in class. Make sure you have your notes written up for this and that you finish the challenge problem to get full credit. Have a good night or day or whatever time it is that you are watching this. Bye-bye.